So today the question that we're going to be looking at is, how can we describe a fictional relationship between two characters in a novel? And so the simplest way you might think to do this is just to assign a single label to each relationship in question from a predetermined set of labels. So a bit of terminology: instead of saying label for the rest of the talk, we're going to say relationship descriptor. So friend and foe seem like two reasonable descriptors. And this is actually fine for a few relationships. So for example, Peter Pan and Captain Hook are foes, Frodo and Sam are friends, but it starts to break down for more complex relationships. So Winston and Julia in 1984, they start out as friends, they're lovers, but then by the end of the book, they're tortured, they betray each other and become foes. In the opposite case, you see Harry Potter and Sirius Black in the third Harry Potter book. There's a big misunderstanding. Harry and Sirius are enemies at the beginning, but it's cleared up towards the end, and they become friends. So obviously, this is limited in the case of relationships that sort of evolve through the course of a book. And so there's one previous work, my co-author Snigdha earlier this year, who extended this to basically model relationships as sequences of descriptors. And so another bit of terminology: instead of sequences, we're going to say trajectories for the rest of the talk. So here's an example below: Tom Sawyer and Becky Thatcher. They start out as friends. But then Becky learns that Tom has been seeing another girl. They have a big fight. They're foes for a while. And then by the end of the book, they're back to being friends again. So this is good, but it still has a lot of limitations. The main one is that we're limited by the fixed set of descriptors that we've chosen. So we can't model anything outside this friend-foe binary that we've chosen. And this work also looks at this problem as a supervised structured prediction problem. And so what this means is that we need to acquire lots of annotations. It's really expensive to acquire annotations, so like what parts in the book are Tom and Becky friends, what part are they foes. And so it's limited to a small collection of plot summaries. So what we want to do is have a model that jointly learns descriptors as well as trajectories. And we want this model to learn these things from the raw text of the books rather than simplified plot summaries. So here's a relationship for which such a model might actually be good. So this is Arthur and Lucy from Dracula. And so this relationship starts out, the two characters are in love, they're about to get married. And so some descriptors that might be representative of this relationship: marriage, love, and joy. So the size of the box here means like how representative it is of the relationship at that point in time. So the two characters are in love, but then Dracula bites Lucy, and so she becomes sick, and eventually she dies. She's buried, but spoiler alert, she's not actually dead. She turns into a vampire. She starts biting little children and generally doing all sorts of bad things. And the end of this relationship, Arthur actually has to stab her through the heart with a stake. So murder may be an appropriate descriptor here. So we see in this relationship things like marriage, sickness, death, and murder are describing the relationship. And these are not things that you would find, obviously, in your friend-foe binary. So we want the model to be able to learn these descriptors as well as the assignments over time. So that's our goal. Before we get into the meat of the talk, why should we care about this problem? So in digital humanities, there is something called distant reading, in which a computer reads a large collection of documents and offers like a high-level summary of something, some particular thing of interest within that collection. So here in particular, we're focused on relationships between characters. And a model that does the task that I just described could be really helpful in answering specific problems or questions like, do Jane Austen's male and female protagonists have pattern in their relationship as it evolves? Or more general questions like, can we detect subtext underlying meals between two characters? So we are sort of theory agnostic. We don't try and propose or support a particular theory, but our model can be used to help gather evidence for a variety of different hypotheses or questions that humanities researchers may have. So with that, we'll get an outline for the rest of the talk. So first, I'll go over the data set that we've collected of character interactions. Then we'll introduce a neural network model to solve the task. some experiments that show that it's actually more interpretable, both in terms of descriptors and trajectories than topic model baselines. And finally, we'll do a qualitative analysis, some good trajectories, bad trajectories, as well as comparisons to an existing annotated data set of relationships. Okay, so I'll start with the data set. So basically, we have a bunch of books, and for each pair of characters in this book, we extract all spans of text in which both characters are mentioned. So what this looks like, this is an abridged version of the relationship between Ignatius and his mother in the book A Confederacy of Dunces. So you can see 3 time steps here. In each time step, there's a span in which both Ignatius and Mrs. Riley are mentioned. These words are highlighted in these spans. In total, we have 1,400 different novels from Project Gutenberg and other sources. We pre-process each book using David Bamon's book NLP pipeline. So this basically does tokenization, co-reference, resolves all pronouns to a particular character in the book. And we define a span as a 200 token window centered around one of the character mentions. So in total, we have 20,000 unique character pairs and about 400,000 spans total. So this is a fairly large data set, so we can use a neural network. And what we do in principle is a recurrent autoencoder that uses dictionary learning to reconstruct its inputs. So before I explain the dictionary learning part, just a review of the vanilla recurrent autoencoder. So this is the 3 spans that we saw before from A Confederacy of Dunces. We map each span to a vector, we apply some recurrent connection, and then we try and reconstruct the input using these hidden states. But we make a slight modification here. Instead of directly reconstructing the input, we put this descriptor matrix, which acts as our dictionary, on top of the hidden layers. So what we do is we multiply this hidden state by this descriptor matrix and then reconstruct our inputs. So basically, each row of this descriptor matrix corresponds to a separate descriptor. So like the first row could be love, the second row could be hate, and so on like that. So this is a pretty high-level overview of the model. Now we'll look at, in detail, the computations that occur at a single time step. So to represent these spans of text with a vector, we use a simple word embedding average. You could probably do more complex things, but we didn't really explore any of the like LSTMs and such. In the next step, we have sort of these global embeddings for characters in books. So Mrs. Riley and Ignatius get their own embedding, and A Confederacy of Dunces gets its own book embedding. So the idea here is that we can store global information about the characters in these embeddings. So for example, Ignatius is always hungry and always rude, regardless of who he's talking to. So we pass all of these embeddings into a feedforward layer, and now we have our recurrent connection. So there's 2 key differences in this recurrent connection from a standard recurrent neural network. The first difference is that we have this explicit linear interpolation between the previous hidden state and the current hidden state. So we initially didn't have this, and we found that it generates really choppy trajectories. So what I mean by that is 2 characters might have been love in the previous time step, but then in the current time step, they were sharing a meal together. And so without this interpolation term, what would happen was that the model would assign, at the previous time step, a really high weight to love. But at the current time step, it would assign a really high weight to food and a really low weight to love. So what this means is that the model was basically saying that if 2 characters are in love and then they have a meal together, they fall out of love, like while they're eating dinner. So this is obviously not true. That's not what we want. And so we had to, and it's an artifact of our objective function, really, but we had to include this linear interpolation term to make the trajectories more smooth and understandable. The second key difference is that we actually use a softmax activation function instead of the common tanh or ReLU. And the reason for this is that we want to interpret our hidden state as a probability distribution over descriptors. In the next step here, we're actually going to multiply the hidden state by this descriptor matrix. So this is basically how you use a attention mechanism in machine translation, except here we're doing attention over this descriptor matrix. And then our objective function is to make this reconstructed vector as close to the input span as possible. So we use a max margin objective with negative sampling. You can read more about it in the paper if you're interested. Okay, so once we've trained this model on our data set, we have this descriptor matrix. So before we can actually interpret the trajectories, we need to first label each row of this descriptor matrix. So because our objective function is trying to make this reconstructed vector close to the word embedding average of the input span, we can actually look at the nearest neighbors in the word embedding space to each row of this descriptor matrix. So here is an example below where the first row here, the nearest neighbors are grenades, guns, and bullets. So you might externally label this as violence or weapons, similar with the remaining columns. Okay, so this is sort of reminiscent of how you label topics that you get out of topic models. And in fact, that's not the only connection to topic models that we have here. So the outputs of the RMN are analogous to the latent variables in a topic model. These nearest neighbor lists from the descriptors are analogous to topic word matrices. Similarly, the hidden states at each time step, well, those are just document topic assignments. And so what this means is that we can now use topic models as baselines on our task. So we have two categories of baselines. One are temporally oblivious. So this means that it treats each span in a relationship as independent of all other spans. So this is obviously not good. But luckily, we also have a temporally aware topic model baseline. So this is the hidden topic Markov model of Gruber et al., which basically models the sequential nature of the inputs. So the document topic assignment at a particular time step is dependent on both the input at that time step as well as the previous document topic assignment. Okay. So with that, we will go to our experiments. The first experiment we're doing is to measure the interpretability of the descriptors and how they match up to topics learned by topic models. So we take, again, from the topic model literature, the word intrusion evaluation, in which we'll present workers with 5 descriptors that come from one descriptor, 5 words that come from one descriptor and 1 word that comes from another descriptor, and we'll ask them to identify which word is the intruder, so which word is from the other descriptor. So we have 2 examples of that below. So in the first case, if you read these 6 words, it's fairly obvious that praise is the intruder word here. But in the second case, there are actually 2 words that don't fit in with this religious theme of the other 4 words. So what happens is when we run this experiment, in the first case, all of the mechanical Turkers will agree that praise is the intruder word. But in the second case, it'll be split among both these words, yourselves and gather. So the first case will get a high coherence score. The second case will get a low coherence score. So the metric we're using is model precision. So this is basically the fraction of workers that agree on the intruder. And we measure this for 10 descriptors, 30 descriptors, and 50 descriptors. So here are the 3 topic model baselines. You see that regardless of the number of descriptors, they all achieve, on average, like 0.5 model precision. So we have 2 configurations of our RMN model. One model doesn't have the global character and book embeddings, the other one does. But you see in both cases that the RMN's coherence is significantly higher than those of topic models. About 0.7. So this is good, and now we can look at some examples of coherent descriptors from both the RMN and the HTMM, which we'll be using in the next evaluation as well. In particular, something interesting is that the RMN learns these highly coherent descriptors about emotions, like sadness and love. Others are like suffering. The HTMM, however, its most coherent descriptors are about sort of concrete things like food or violence or boats. Emotionally, it's a bit lacking. It learns a couple topics about love that are sort of like duplicate topics. Even after cross-validating the parameters, we found that all of the topic model baselines tend to learn a lot of duplicate topics, specifically about love, so no other emotions. Okay, so the next experiment we do is to measure the quality of the trajectories. And so before we get into the experimental design, I just wanted to, as a brief aside, show you how we visualize trajectories, because we iterated for a number of different visualizations before finding one that our Turkers could actually understand and do the task well. So this is fairly simplified, but basically for all the time steps, in a particular relationship, we have this distribution over descriptors, so we'll just take the argmax at each time step and stack them up. So as a concrete example of this, here's a synthetic relationship that I created. It has 5 time steps and 4 descriptors. So the first time step, love is the argmax of that row, so we put love down here. Second time step, love is also the max. But now, maybe the 2 characters in question are having financial difficulties, so money appears. They might have resorted to a life of crime, and eventually things don't go so well, and the relationship ends tragically. So that is an example of how we create these visualizations. Now we can move on to the actual task. So we present workers with 2 of these visualizations, one for from the RMN and one from the HTMM, and we also present them with a plot summary that describes the relationship in question. And we ask them, which of these 2 visualizations better captures the content of the summary? So this is fairly subjective, as we'll talk about later, but we have 125 of these character pairs to evaluate after crawling through Wikipedia and removing uninformative summaries. And we find that workers prefer the RMN's trajectory to that of the HTMM 70% of the time, and this is a significant result even after correcting for random chance. So here's an example of something that we would show the Turkers. This is an actual example from the task. This is the relationship between Siddhartha and Govinda from the book Siddhartha. So we see here below the summary in which both character dimensions to their names are highlighted. So the first, I don't know if you can read that, but the first trajectory goes something like affection to love to education to worship to fantasy to religion, while the second one sort of stuck for most of it in this royalty descriptor, which isn't really described anywhere in the summary or the book. So this is a case where all of the workers agreed that the first visualization, which was generated by the RMN, was better than the second one, which was generated by the HTMM. However, in many cases, the differences aren't this obvious. There might be way more subtle differences, and this reduces the agreement between workers. So we'll see examples of that later. Okay, so now we'll move on to the qualitative analysis. First, we'll look again at this example that we saw earlier, Arthur and Lucy, where we know the ground truth looks something like marriage to sickness to death to murder. So we'd like the model to output something like that. So here's what the RMN and the HTMM learns for this relationship. So the RMN, after starting out poorly with boats, moves on to love, sadness, suffering, murder, with some other descriptors thrown in there. But it's generally doing a fairly good job of modeling these arcs. However, the HTMM is predominantly stuck in this love state, totally is ignoring the whole vampire thing and biting little kids and whatever. So yeah, it's not doing a very good job. With that said, there are a lot of cases in which both these models agree, and this is primarily on concrete or events-based descriptors. So here we see a trajectory visualization where both models agree on things like clothing, food, sex, and boats. In general, this is true of most relationships. The models generally assign these descriptors to similar places in the trajectories. Here's an example of a failure case. So this is a relationship between Charles Darnay and Lucy in The Tale of Two Cities, which is, has a fairly sad tone. And so you can see that the RMN is predominantly in a sadness state, while the HTMM is, again, doing its love, 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 love thing. But that is actually accurate in this case. It turns out that Charles Darnay and Lucy are in love for this entire book, but they have a lot of bad things happening to them. And so because we're using just the argmax in this visualization, we're sort of ignoring maybe there's a love descriptor here that's not the max, but it's still highly weighted, and it's just not shown in this visualization. Okay, so our last bit of analysis here is going to compare to annotations in this data set released by Philip Massey and others last year. So basically, for a lot of relationships in Project Gutenberg, they've annotated them with, among other things, positive, negative, and neutral affinity annotations. So we map 120 of these manually to relationships in our data set. And so since these annotations are at the relationship level, we don't have a label at each time step, we have to aggregate, so compute one vector for all positive relationships and one for all negative relationships. So our goal is to figure out what descriptors are most likely to appear in positive relationships versus negative relationships. So what we do is we concatenate together the trajectories of all of the positively labeled characters. We do the same thing for all the negatively labeled characters. So these are just example numbers here. We just compute an average. So this is a very simple, we could probably do something smarter, but we just average them together, and then we rank the descriptors by most positive and most negative. For more details, you can read the methodology in the paper. But the most positive descriptors on our actual data set we find are things like education, love, sex, parental, and most negative we see murder, sadness, violence, and crime. But in particular, politics is highly negative for both the RMN and the HTMN. So we were really interested in why this was happening. So we looked at the data set and we found that most of the annotations we were using come from Victorian-era novels, so such as those by Charles Dickens. So doing a search for literary scholarship about this, we find that Victorian-era authors are obsessed with autocratic and dictatorial, abusive government. This isn't just true of Victorian-era authors. Science fiction authors, for example, tend to write much more about dystopias rather than utopias. So this might be one reason why politics is very negative for both of these models. All right, so before I conclude some areas for improvement, before we can actually use this model to help out people in the humanities with questions that they might have. First of all, as you might have thought while I was going through the experiments, it's very hard to evaluate these, this model and unsupervised models in general. Specifically here, when we're comparing two trajectories, what makes one better than the other? If one trajectory hallucinates an event that didn't actually happen in the source text, but another one ignores a key event, which one is better? So this is actually a very hard problem, and hopefully we'll come up with some better evaluations that let us know, like, actually when we make a tweak to the model, is it actually improving things or not? The second thing is that we're leaving out a lot of information by just looking at spans of text in which both characters are mentioned. So we're ignoring all spans in which just one character is mentioned and the other one isn't. And we could take this to the limit and argue that the entire book contains clues as to the relationship between a particular pair of characters. Finally, our model's performance depends on the quality of the book NLP preprocessing that we use. So in particular, book NLP is not very good, and most coreference systems in general are not very good at disambiguating first-person pronouns. So if I have a first-person narrative, the RMN currently is missing a lot of spans that would actually be very useful in characterizing the nature of the relationship. And so any improvements on this front would directly improve our performance on first-person narratives, at least. So to recap, we introduced this task of unsupervised relationship modeling, and we introduce also an interpretable deep architecture, the RMN, for this task. We find that it generates more interpretable descriptors and trajectories than topic models. And currently we're talking with a professor in the English department at the University of Maryland to actually use this to help her research out. In particular, she's interested in looking at subtext. So because our model generates probabilities at every time step, we can actually look at characteristics of relationships that are sort of bubbling below the surface. So yeah, that's it. And the code and data are available at my GitHub. Yeah, thanks.
Hi, so I'd like to, first of all, congratulate on the really interesting work. I'm thinking here about the relation between this kind of model and graphical model approaches. You compared with topic models,
right?
But there's been some work in dynamic topic models where topics may change over time or where topics at different points in a text collection it might have there might be different parameters.
Right.
So I wonder whether the topics might evolve through the book if you used a dynamic topic model, or if you could capture the same notion of progress in the relationship. One interesting property that graphical models have that the feedforward networks don't is the future can influence the past. And can feed back down to the way that you read particular passages. So you get kind of more global decode of what's going on in the novel. And I wonder if you've seen cases where that would have been useful.
Yeah, so actually, initially we started this out, related to what you were saying, not as an autoencoder, but as a predictive model. So at one time step, we would try and predict the state of the relationship at the next time step. I think this is sort of similar to what you were saying with capturing sort of global information. However, it didn't work. We weren't able to optimize it properly. But yeah, I think that's an interesting idea. Another point I want to make is that we could certainly use more different topic models, but I think one of the advantages of the neural network framework is that we were able to add in a lot of prior knowledge in the form of these pre-trained word embeddings, and so I think that directly contributes to the better interpretability of this model versus topic models. And I guess there's been some work on adding pre-trained embeddings to topic models, but yeah.
So I guess my question was the same. It's about things in your life, the relationships stages don't just follow one another without a logic, right? One thing causes another, or one thing plus some external circumstance cause another. So I was wondering if you did just bigram analysis instead of unigram analysis and just look at or pointwise mutual information or something between the successive stages, whether you would find anything, or whether you could use the fact that there should be, unless you're in a soap opera where it doesn't matter what the hell the logic is. You look and you use this in order to say, I'm missing something because I'm not able to predict what happens, what comes next, or what came before. So I need to find external stuff and feed that in. You didn't do any of that kind of analysis.
Well, I think theoretically the recurrent connections could handle that maybe, but yeah, we didn't look at anything from the future influencing the current time step. So yeah, that would be an interesting thing to try.
Hi, nice work. So I'm not very familiar with the topic models you use for baselines, but one thing I noticed from your examples is that even when it performs better than your method, it still gives like quite coarse trajectories, while your method gives much more fine-grained. So do you know why is that the case?
I am not sure why that's the case. One of the things we looked at is, so in the examples here, we show trajectories that are, so like on the case on the right, where the HTMM has produced or has put this relationship in the love state for a large period of the relationship, whereas the RMN has more changes in the relationship. But I think in general this isn't the case. Most of the trajectories look like the one on the left, where both of them are changing changing the maximum descriptor at about equal frequencies. Yeah.
Thanks. I wanted to ask a little bit about the first experiment, and in particular, so effectively what you're doing here is each of these, columns in your R matrix are points in your word embedding space, which came from, whatever the training corpus.
Right.
And so, on one hand, a really interesting baseline would be just if you pick a point from that space, uniformly or Gaussianly or whatever, is the cluster of words around that point, do people find intrusions? So as one of the people who worked on putting, word embeddings into topic models in the past, we sort of argued that, no, that's the whole point of these spaces, is they've got a lot of sort of semantic coherence.
Right.
So if that's true, What is the difference that you observed between the two variants between, I think it was the different numbers of clusters in the model where, if you go back to your results, those two. Yeah, the difference between the pink and the orange.
Oh, so these are two different configurations of the model, but...
Right, but why, if these are effectively just points somewhere in this sort of already pre-constructed semantic space, why are those differences meaningful, or is this just sort of the real size of the error bars?
Oh, so you mean why they... Well, they... right. So I think you can even see here that with more descriptors, you get less variance between the different intrusion trials. So it is the case that when you train with like 30 descriptors, at every run you get many different descriptors that you might have not seen in the previous run. But with 50, a lot of them are about the same. So what happened was we initially did all our experiments with 30 descriptors because it's sort of expensive to run these evaluations. But after the reviews came in, we did this with 50, and we figured that after seeing this result, we probably should have just stuck with 50 to begin with. But yeah, I don't know if that totally answered your question.
Thanks.